All right. Thank you very much, everybody, for coming. We have a lot of slides, so we're going to go right into it. My name is Huang, and we have our colleague, Roman, with us, Fernandez. We work for Armorize Technologies. I'm co-founder and CTO to Armorize Technologies. So today we're going to be talking about Drivesploit, circumventing automated and manual detection of browser exploits. What's up there is the Chinese wording for drive-by download, which actually existed for many years before the term drive-by download came about, because this type of attack was quite prevalent in Asia. I was doing research. I was doing black box scanners at that time, and we weren't able to crawl a lot of the web pages because of the dynamic content. So we started to embed IE, and we wanted to have mass crawling and SQL injection results. We had many crawlers crawl for many days, and then the end result was all of the boxes ended up with malware in it. We're like, oh my gosh, so what happened? So actually, we submitted a paper to the WWW conference in 2002. In the paper, we described how we embedded IE, and because we had to embed IE, we had to sandbox IE in order to prevent these exploits from attacking our IE. So that was how this technology started. The slides are not in your CD. Apologize. It's right now on SlideShare, so if you go to www.drivesploit.org or you follow the Twitter, you can download it right now. So today we're going to be showing one type of browser exploit, which is the drive-by downloads. Let's define that. So hackers distribute malware by poisoning legitimate websites, and what's typical is they inject malicious iframes into HTML content, malicious iframes into legitimate HTML content. And the affected websites essentially become a delivery mechanism for malware. They appear normal, and the victims do not need to click or agree to anything. They simply connecting to the infected website executes the attack. Recent incidents include the Aurora incident, which began sometime in June last year until February of this year, when Google reported and the news went to the media. It was a targeted attack. It used the IE 0-day and was confirmed publicly by Google, Adobe, Juniper Networks, and Rackspace, and a total of 34 organizations were targeted, according to coverage on media. A recent one, DNF 666. If you haven't heard of this, you can go to our blog. Just Google for the keyword. It started since March 2010, initially leveraging an Adobe 0-day. The victims included Wall Street Journal, Jerusalem Post, and then we later found out that all of that effort was just to steal online accounts to online games in Asia. So the second wave and the third wave targeted only Asian websites, while the first wave hit Wall Street Journal and Jerusalem Post. And it happened to CNN, GameSpot, US Treasury, Sony PlayStation, Washington Post in the past. So let's dissect drive-by downloads. What happens is very simple. The visitor links to an exploit server. The exploit server serves him a legitimate page, but it includes a browser exploit and also a payload, or what we call downloader. The exploit, and this part is usually obfuscated. So when it executes, it will deobfuscate itself, and then it will exploit the browser. And at this time, the dropper will execute, which is the payload or the shellcode. And it will cause the browser to link back to the malware server. And the malware server, which is usually different from the exploit server, will distribute malware back. And then finally, the malware will link to a CNC. And that's basically the attack. It's very simple. But now the key is, who would visit a exploit server? Nobody would. So the key here is traffic. And actually why these two servers are usually separate is because, at least in Asia, it's two ecosystems. There are people, there are groups responsible for developing the browsers, and then developing the browser exploits, and then there are groups responsible for getting traffic to the exploit servers, and then there are groups responsible for developing the actual malware, which is quite hard because that malware has to bypass antivirus. And so what happens is you would typically, the attacker would try to infect one of the very high traffic websites, what Google calls the landing website. And then so from there delivers a URL generator, which is a piece of JavaScript that generates iframes or JavaScript sources typically. And this iframe would then cause the browser to start loading content from the exploit server. Recent incidents, DNF 666, and then in May to June, there was mass shared hosting compromise, which included GoDaddy, Rackspace, Network Solutions, Bluehost, and DreamHost. Some of these, after being compromised, wasn't used to serve drive-by downloads, but instead other types of malware, such as fake antivirus. But some were after compromise, we're serving drive-by downloads. And then this is a part of a very typical continuous targeted attack, the same incidents to Aurora, that basically is a persistent threat. That's a continuous threat. And when this happens nowadays, it's very easy. It's very hard to remove because a lot of times the URL generator is inserted not into just a plain PHP file, but it would disguise itself as a legitimate WordPress or Joomla file, or it would insert itself into a WordPress store procedure or a Joomla somewhere in the Joomla database. So and it's going to take you a lot of time and a lot of SQL commands to dig that out. And all throughout this time, you wouldn't know how to remove that malicious iframe or malicious JavaScript from your website, and that makes you look very bad. And that was all we've talked about so far is only one type of malicious JavaScript injection, and that is when they physically tamper your data. Another type is when they don't physically tamper your data. Typically, what happened for many years in the past in Asia is attacks coupled with ARP spoofing. So, for example, the ZXARPS tool is very, very mature, very robust. If the attacker is able to compromise other machines on the same lane segment as your web server, they may not choose to infect the web server directly because it then is very easy for you to find the injection and fix it. They would compromise another machine that can do ARP spoofing and then would use a tool like ZXARPS to act as man in the middle, and then it would become the man in the middle, and then it would just basically be passing traffic through, but for every HTTP response that it gets from the server, it would inject a malicious script or iframe and then pass it back. So in that case, you think your visitors tell you that your website is compromised. You go in, you dig the database, you dig the files, you don't find anything. Well, because they haven't tampered anything. In March 2009, what happened was websites like tw.msn.com and taiwan.cnet.com and other sites was attacked and embedded with malicious content. And down there you can see a Cisco advisory regarding it. The incident lasted a total of 12 days before it was totally contained, because what happened, as we figured out, was the injection was in the middle of the route. So it wasn't on the lane, it wasn't on the web server itself, but it was on one vendor's equipment that was a Layer 4.7 equipment in the middle of the route that was compromised and that was used to inject the iframes. So this is the second type of this type of attack. So now we're going to do a live demo using dig, using a persistent cross-site scripting vulnerability in dig. They have fixed this vulnerability already, but our link is still there. So let's go to dig first. Firefox, where are you? Oh, lovely Firefox. Okay, there we go. Safari. That's all right. Okay, so usually when you view one of the dig pages, what you see is this. You would see the digged link and the description and people who dug it, this kind of thing. But let's look at the source code. Oh, jeez. There we go. All right. And here you would see that, let me just zoom it for you because the room is so big. That includes www.zcrack.org/g. And it's included as an iframe source, right? As you see here, which shouldn't happen. So it's a very simple persistent cross-site scripting that exists in dig, and the attacker, who is us for the demo, has used that to inject that iframe. So let's start our Drivesploit. Okay. So we've implemented the Drivesploit framework on top of Metasploit. So now I'm starting Metasploit. Get this window smaller. And let's, exploit. And let's go to the victim machine. Visit the dig URL. Okay, so as you can see, Metasploit serving, and we've chosen to use Meterpreter as the payload. And now Meterpreter is starting a new process in Notepad and migrating itself into Notepad. It's completed. Okay, so as you can see, the Internet Explorer is gone, but we now have an open session. Connect to it. See all the processes. So we basically have now a shell into the victim's system. So let's just kill ourselves. And it's attached to actually another process, notepad.exe, so that even though IE is dead, it's all right. So I'll kill myself. Okay. So that's basically a very simple demonstration of a typical drive-by download process. So what happened was Dig had a persistent cross-site scripting vulnerability. The attacker used that to inject the iframe, and in the back end, Metasploit or Drivesploit was used to serve the JavaScript exploit. Okay, the motivation behind building this. Armorize provides solutions that monitors websites and detect malicious contents 24/7. We use multiple behavior, heuristic, and signature-based technologies. Most technologies are developed on our own, but we also integrate antivirus because behavior-based technologies that we use are very, very costly. And when you have to scan millions and millions of URLs a day, you end up paying hosting companies a whole bunch of money. So we started a while back looking if we can find some antivirus solutions that can be coupled with our behavior analysis. But they're very, very expensive. And so we spent a lot of time testing our own technologies and also selecting antivirus technologies. And the key to this type of testing is how good are we and them at detecting new drive-by downloads instead of old ones. But how do you get new drive-by downloads that don't exist? That's a problem. So we ended up getting the old exploits and then mutating them by hand to generate new exploits, and then testing out all these antivirus technologies in our own. And we ended up writing big messes of code. It was very hard to debug, and it was just taking us a lot of time. So we needed a good framework to help us replicate, manipulate, and mutate exploits found in the wild. Note we didn't say obfuscate. There's a difference, because when we say mutate, we're changing the raw basic JavaScript exploit in its raw form, and not in its obfuscated form, into new derivatives. So Drivesploit is born on top of Metasploit. Initial findings. Antivirus capabilities differ greatly. Desktop and API versions differ greatly in performance, meaning that an antivirus technology which really performs well for its desktop version may perform very poorly for its API version, which is the version that we want to use, right? It's basically a library or a console or an API for us to call. And also cost is not equal to performance. Surprisingly, the most expensive ones may not be the ones with the best performance, at least according to our testing. And so antivirus versus drive-by downloads. So we ended up getting quite confused, and we started calling these antivirus companies, and we were like, the results don't make sense, blah, blah, blah. And like, well, what are you testing? Well, we're testing JavaScript. And then they don't want to answer the call. And we call again, and we're testing JavaScript. Well, can you give us some explanation? Well, JavaScript is sissy stuff, We don't. So JavaScript to them is not hardcore stuff. Maybe it's true, right? I mean, yeah, PEs and everything and assembly, these are very hard. But unfortunately, we have to deal with JavaScript when we deal with drive-by download. And so, according to their explanation, as you can see, in our drive-by download process, the URL generator is JavaScript, the exploits are JavaScript, the malware itself is the PE binary, and they'll say, and this is what they said. Well, we'll detect this part. So during the drive-by download detection process, if in the end that's going to exist and we're going to detect that. But unfortunately, that's not the case. Why? Because usually a malicious domain serving that piece of malware is going to be taken down 2-3 days later, but the injected domain, such as dig.com, the injection is still going to be there for a long time. And although that piece of malware is not valid anymore, is not active anymore, we still want to be able to detect that. The other thing is, nowadays, a lot of DNS, a lot of ISPs, when they find out that domain is malicious and serving malware, would block that domain even though that domain is still active. And then sometimes it's just the in the economy, the subscription period is over. You bought you paid us to serve for 2 days. It's now past the period. You haven't paid up, so we're temporarily shutting it down. That doesn't mean that we're not going to reopen again. And so we want to focus on all of the JavaScript. And that's why we can't just rely on PE detection. So the deal here is ECMA scripts, which is JavaScript, VB script, Adobe JS, and ActionScript. And so we want to take this part out. Okay, we want to take this part out and replace the exploit server with Metasploit and use Meterpreter or something similar as payload, which basically does memory injection instead of trying to download a piece of malware and writing it to disk and have that malware do the malicious stuff. We want a payload such as a Meterpreter, which also exists in the wild. And so that we can test this out, and we can test out the abilities of technologies just detecting the injected JavaScript or the JavaScript exploits. So drive-by downloads, what do they want to do? They want to avoid detection at the victim's desktop. They also want to avoid detection by UTM's gateways. And they also want to avoid detection by automated monitors, which are services like those that we provide, or live for as long, and they basically want to live for as long as possible. So, conclusion. What are you going to do? First, reduce exposure. And you do that by selectively. Serve selectively. For example, you can serve only to each IP only once. You lock the IP that you've served to. Because if the visitor visits you for the first time and your exploit doesn't succeed, forget about it, right? But don't serve to him the second time because he might be somebody working at an antivirus company. Avoid detection and analysis. Then you got to mutate well. So Drivesploit basically is trying to mimic these two goals of drive-by downloads. Serve selectively. So at the HTTP level, this is what we implemented into Drivesploit. Serve only to fresh IPs. Serve only to particular referrers. This happened to the Gumbler mass SQL injection that happened in Japan. And few security vendors were able to detect this on the spot when it exploded, because Gumbler was very selective about the referrer. It only served to referrers from Google. And in our case, in our example, for example, since we've infected dig.com, we can also specify, well, we are going to only serve to referrers coming from dig.com. Makes sense, right? If you're connecting to us directly, sorry, you're not somebody that we want to infect. We want to keep our 0-day for a bit longer. Particular agent strings, so that we only serve, if this exploit is for IE7 only, we want to serve to IE7 only. If you connect with the Firefox, we want to serve to you. If you're a Google crawler, if you're a Yahoo crawler, we don't want to serve to you. Blacklist. Blacklist of security vendor, well-known crawler IPs and security vendor IPs. We don't want to serve to those. And that basically covers the first part, which is serve selectively. The second part, script mutation. This part is for both the exploit and also for the payload. The goal here is not to obfuscate. A lot of JavaScript exploits has been using existing JavaScript packers, but that's very easily picked up by antivirus. So the new ones all don't. The goal is not to obfuscate, but it is to mutate the raw form and bypass signatures. So we want to try not to have fixed components when we generate the JavaScript code or the new mutated JavaScript code. And we want to try to use common operations. So we don't want to use rare operations that nobody used, because then antivirus can say, well, this operation, only 0.01% of JavaScript use those, and they're mostly exploits. We don't want to have those. So this is basically what makes up of a JavaScript exploit. There's a shellcode, there's the memory correction part, heap spray, and trigger. This is how a piece of shellcode looks like. Basically, just a very long list of strings, which converts to bytes. This is the memory corruption part. Oh, we're using IE peers as our example here. Memory corruption part, and we're using the exploit that's provided by Metasploit for IE peers vulnerability. And this is the heap spraying part. And finally, this is the trigger. This is the actual trigger that would execute the piece of malicious JavaScript. And then usually this whole part is sometimes, especially in the old days, obfuscated into a big blob, and then deobfuscated. So there's the obfuscated form and there's the primitive form, as we've mentioned in a previous slide. And so you would start with the trigger, and the trigger would then cause the deobfuscator to deobfuscate the blob, and then execute the the heap spray and then the memory corruption. So with this entire part, the primitive or raw form, we want to mutate, and then for the triggering part, we want to prevent in case we are inside a sandboxed or detection environment. So we want to know if we're inside a sandboxed environment, then we want to prevent ourselves from executing anything. So mutation features implemented so far. We've implemented 5 main features so far. One is JavaScript random variable auto replacement. It accepts a piece of JavaScript. It parses the JavaScript according to the JavaScript grammar. It identifies all names, including variable names and function names, and it auto replaces those variable names and function names with random names. There is already a class in Metasploit called obfuscate.js that does similar things, but you have to identify all the names yourself for it, which is very error prone in our testing process because sometimes we just miss some variables or function names. And also when we do that, it just creates a big mess. So we want to have one function call and say, this is a piece of JavaScript. Replace all the variable names and function names with random variables of our definition. We want every random variable to be of 4 to 10 characters in length. So right now it's all random. We're thinking about adding a dictionary to it so it doesn't look strange, right? If a dictionary of, 1,000 words, that may work. And passes back the new JavaScript and a vector of old new name mapping. So you know which of your variable is replaced with which name. And this is how you actually use it in Drivesploit. The second one is very, very commonly used. It's called JavaScript concat string obfuscation. So this is how you use it. Basically, you call it, and you give it a piece of string, which can be the shellcode. And this is Metasploit, as you know, has a lot of encoders already. But when you're putting shellcode inside JavaScript, you have a lot of ways to further obfuscate that piece of shellcode because you can execute JavaScript. So this is a very commonly used but very effective algorithm, and that is I give you a piece of JavaScript, a piece of shellcode, and then you split the strings, and then you generate JavaScript that add the strings back and pass me back the JavaScript. So I'll show you how this works. This, for example, is our shellcode string. We would randomly chop it according to how you want us to chop it. So, for example, chop every 4 to 8 characters. And we randomly chop it into segments. We would then assign the segments to variables, okay, to layer 1 variables, and then we would scramble these assignments so that they look like this. All right, so now as you can see, the middle section appears first. This makes it very hard for heuristic-based pattern-based detection algorithms. So that's layer 1, and then we would do layer 2. Right? We will add these. We would then add these two together into layer 2 variables, and then we would then again scramble these. Okay, and we'll continue until we added everything together. So finally, this is a script that will be passing back to you. Of course, all the variable names are going to be randomized. They're just put this way for easier reading. And D1 is underlined because we're going to give you this whole new chunk of JavaScript and the variable name so that you know that that variable name in the end contains your shellcode string. The third one is JavaScript random text insertion. And what it does is it's also very commonly used in the wild. What we want to do here is the goal is not to beat antivirus. The goal is to simulate what's being used in the wild so that we can compare technologies. So this function call would ask us to ask Drivesploit to generate a random four character string and then insert into the original string for every 6 to 10 characters. And then we'll return you the new string. And number 4 is numeric literal mutation. A lot of times, JavaScript antivirus is sampled by these fixed numeric literals. And so we'll have a function that's a slash space. So basically, you pass us a numeric literal or a hex code. And we would then randomly generate a computation that computes back to this hex code or byte, to this byte, right? So that your JavaScript, every time you serve to a new visitor, your JavaScript is going to look different every time. Well, that's basically what happens in the wild, so we want to simulate that. And so before, your JavaScript code would look like something like this, the line above. Now your JavaScript looks something like the line below. Okay. And then for the triggers, so we've covered Drivesploit for the first part, 5 features for mutation, and now for trigger prevention. So we want to know if we're in a sandbox environment, and if we do, and if we're not in a real human's browser, we don't want to execute. And this can be done a lot of times. You see that the trigger function is set on event handlers div unload and image unload. You see more image unload these days. Anybody want to guess which one is more effective? Div? Who think it's div? Who think it's image? Okay, a lot more people for image. Somebody say why? All right, come on. Why? Yes. The answer is yes. The answer is image unload is more effective, but why? It's yes. And the other reason is, the right answer is image load. Image unload is very effective for some of the newest and very accurate technologies, for example, ours. Div unload is very effective for older technologies that do not implement the DOM. Okay, so basically you take SpiderMonkey or Rhino and use it as your JavaScript interpreter. These JavaScript interpreters don't have the DOM. Newer technologies like JS Unpack or VeriSign implements the DOM objects themselves, right? So if you're only using a JavaScript interpreter, because it's very hard to reuse IE, so typically we use some versions of Firefox, or just some versions of either SpiderMonkey or Rhino, some versions of open source JavaScript interpreter. And div unload is very effective for that, for the older ones, because they don't have the DOM. They don't have DOM implementation. Image unload is effective for technologies that really sandbox IE and run IE as the detector. And the reason is because, IE has image unload, but what happens is when you're crawling millions of pages a day, this introduces a lot of bandwidth. And bandwidth and loading big images is just very, very costly. And so there's a feature in IE to disable image rendering, right? You click on Tools, Options, and you can disable image rendering. When you and some vendors do that, and when you disable that, image unload doesn't fire. Okay, so they pretty much figured out what these detectors are, what these detectors are doing to detect them. A third one is also very commonly used. It's just some do-while loop, some arbitrary do-while loop. But if you see here, what's here is in a do-while, there's an extra semicolon, which is actually a grammatic error. But IE is so smart that it can recover from that and continue, while SpiderMonkey or Firefox just throws an exception. So if you're using some versions of SpiderMonkey, it would throw an exception and then it wouldn't execute. While if you're a user using IE, and if I'm serving you an IE-based IE exploit, then it would work just fine. Oops. Sorry about that. Okay, so we implemented some of these, and then we tested it out. So we implemented these in Drivesploit, and then we generated the XML files, and then we uploaded them to VirusTotal, and we used IE peers as the JavaScript exploit. The plain IE peers on VirusTotal hit 17 detections. And randomizing variables, although it was pretty hard to do, considering we had to parse JavaScript, wasn't really effective. So in Taiwanese, we call this bo cai. It means too bad for us. When we used random text injection into the shellcode itself, we brought this down to 13. So from 17 to 13, which is good. When we use random variables plus string shellcode string injection plus concatenation, meaning splitting it up, we ended up with 11 out of 42. So from 17 down to 11. So at this point, we pretty much thought that since we reduced 6 of them, we pretty much thought that roughly 6 of these antivirus detectors were based on the shellcode itself. Okay, so when we completely scrambled the shellcode, we only bypassed 6 of them, while the others was also sampling the rest part of the JavaScript, which included the memory corruption part and the heap spray part and the trigger part. And so when we used concatenation of shellcode plus the rest of the code, it came down to 1 out of 62, which was very good. Oh, which one? It's down here. It happens to be down here, so it happens to be down here. And this one, to be honest, is very good. Okay. And when we used injection of the shellcode plus concatenation of the rest of the code, just these two simple combinations were down to 0. And adding random vars, of course, the same. But VirusTotal uses versions that we use, which is the API version or the console version. But antivirus desktop versions is much stronger. Why? Because they can monitor host environment, they hook into browsers, so it's easier for them to get the raw form of exploit. If you hook into the browser, you can see exactly what the JavaScript engine is doing if you hook deep into the IE JavaScript engine, and as soon as you create a new variable with a raw form of shellcode, then I can say, boom, you're an exploit. So, And they can also do behavior analysis. For example, buffer overflow behavior or download to file behavior, which makes detection a lot easier. Okay, so this is the result of our limited testing of Drivesploit against these antivirus. We listed out, we abbreviated, you can guess. And we tried out the big ones. And as you can see, there was one vendor which Drivesploit could not beat. And as we use more features, for example, concatenation of the shellcode plus concatenation of the code itself, or injection of the shellcode plus concatenation of the code itself, we start to beat more and more antivirus. There was one vendor worth mentioning, and this vendor, as you can see, it has 2 scores because the static part wasn't that good, meaning that if we put all the HTML files that's generated and we asked to scan the folder, it couldn't find a lot of the exploits. But when we actually run the IE and have Metasploit served to us, then it basically using its HIPS, host-based intrusion prevention system, it was able to detect every one of them doing buffer overflows. Okay. So we're originally going to do a demo to show you how, as we add more triggers, we can bypass, add more of these features, we can bypass most of them, but I think we're going to be out of time, and we'll leave time for some questions. So finally, again, this is to be triggering behavior-based encryption. When we turn on this feature and we submit to Web, for example, it doesn't find anything. And what happens is, if you change our eval into alert, and you alert it in Firefox, it doesn't show you anything. Okay? But you alert in IE, and it shows you the actual, what we're trying to do, the exploit. So what we did is we said, okay, we're going to encrypt our exploit with a key. And that piece of key can only be generated if you are the correct target browser. So if you're IE7, then if this exploit is for IE7, then only IE7 is going to be able to generate that key. So as you can see, every browser has a lot of different features and different behaviors. The rendering of CSS is very different from every minor versions of browsers. So we implemented a lot of checks based on CSS rendering, based on HTML parsing, based on JavaScript differences. All these, we put all these together, and we came up with a lot of checks. So you would say, okay, this exploit works only for IE6. Give me an encrypted version of my JavaScript exploit, and give me JavaScript to generate the decoding key. And the key is only correctly generated if JavaScript is run under IE6. So what we would do is we would say, okay, in order to correctly detect IE6, we're going to use this subset of our checks: 1, 3, 4, 6, 8, 9, 12, 14. All right, and we're going to generate, we're going to assign them to each variable. We're going to generate this piece of JavaScript to be served together with the exploit, and then we would generate the correct answers. If you are IE6, the correct answers should be those. And then we would scramble it up. So as you can see, the R value is scrambled up, but the L value, which is ABCDE, remains the same. And that effectively scrambles up the bits, the correct bits. Which means, although we're serving to a lot of IE6, we're generating a one-time key for every browser. So it's not like IE6 always has the same key, right? Because of this randomization. And so we'll use this as the one-time key, and we'll encrypt, and we'll use server-side script, which in case Metasploit is in Ruby, to encrypt the JavaScript using that key. And then we'll generate this piece of decoding JavaScript. Of course, all the variables are, again, going to be randomized. And so this effectively is very, very effective right now against most behavior-based technologies, because unless you're running the exact version of IE or operating system or what have you, then you're not going to be able to decode this piece of JavaScript. So, conclusion, why is it so hard for antivirus? Because antivirus is designed to install on desktops and notebooks. So desktop and notebooks have very complicated behaviors, strict resource complaints, and therefore AVs and gateway vendors rely on signature-based technology that has to be lightweight and accurate. But JavaScript, especially drive-by downloads, are just indisposable JavaScript. They're generated every time that they're served. Disposable PDF script, disposable ECMA scripts, basically. And JavaScript packing is the norm. So you can't say every time you see a packed JavaScript, you're seeing something malicious, because people love to pack their JavaScript because they don't want their source code to be taken sometimes. Google has JavaScript packer, Yahoo has a JavaScript packer, and Bing AdWords that everybody uses. And so it's very hard to just use heuristics and say, packed JavaScript is malicious JavaScript. Okay, how about behavior-based, such as Honey Client, Sandbox, SpiderMonkey, Rhino, JSONPack, Web, Python Honey Client? Well, use VBScript, for example, is an effective way. We haven't demoed it here. Don't serve to detectors. We demoed this part. Fingerprint-based encryption, and also very little but effective techniques. For example, sleep for some time, right? Because if you have to scan millions and millions of pages a day, if you're Google, you don't have time to wait for 3 minutes to see if some JavaScript executes or not. And so that one line can be pretty effective. Oh, well, it's not sleep, it's set timeout, but it's the same concept, or time lock puzzles. So future work, what we haven't implemented here that is very widely used is randomly chop up scripts and split into individual files, generating VB script instead of JavaScript, encrypting using data existing outside of HTML, for example, HTTP headers, so that you can't submit that piece of HTML to an antivirus vendor, because the key to correctly decrypt itself is in the HTTP header, which is not a part of the HTML. So all these are future work, and Drivesploit is open source, and we really are looking for contributors to join us. Discussion. The talk that we heard this morning by Eckersley of EFF basically said that 94.2% of typical desktop browsers are unique, can be uniquely fingerprinted. As you know, drive-by download is widely used in targeted attacks. So if the percentage is that high, because in targeted, what people don't understand about drive-by downloads is it's not the technology. It's not why drive-by downloads are used effectively in targeted attacks. It's not only because of the technology. What's a targeted attack? It's targeted, meaning you're a targeted person that the attacker wants to attack. You call your colleague and say, hey, I want to know this data. Can you send me the email right away? The attacker knows about it somehow immediately and sends you the email immediately with a drive-by download. That's a targeted attack. And this happens quite a lot. And so in a targeted attack, this actually can be used, because you should have enough knowledge about your target to know what his browser is, and then you can encrypt your exploit so that that very few browsers other than his browser in his environment can decode your piece of JavaScript. And that ends the talk. I'm sorry we're out of time for questions, but I'll be here to answer your questions. Thank you.